I'm George Mirza, and I'm going to go through the first problem of the final learning assessment. For the first part of it, what is the relative humidity where water condenses? That is pretty simple. It would be when the partial pressure over the vapor pressure is greater than or equal to 100%, because that represents the point where the actual pressure of the air is equivalent to or greater than the saturation pressure of water. So yeah, pretty much if you raise temperature, you increase the amount of water that can be held in air, and then if you just decrease that temperature, the amount of water in the air can no longer be held, so it has to condensate. All right, so for the second part of this problem, how much mass of water vapor can air hold at 50 degrees Celsius? All right, so I'm just going to write down the givens really fast. Okay, so to begin, this is everything that we need to solve the beginning of this problem. So the first step is going to be solving for B1 at 50 degrees Celsius, which that is just the specific volume. And in order to do that, I'm going to take the known specific volume at standard temperature and pressure of air, which is 0.816 meters cubed per kilogram, and then take values that I got from the steam tables for the reduced pressure of both at the standard temperature and then also the reduced pressure at 50 degrees Celsius or 323 degrees Kelvin. Okay, after doing all of that work, I come out with the final answer of a specific volume of water at 50 degrees Celsius, or sorry, of air at 50 degrees Celsius is 0.536 meters cubed per kilogram. So I'm just going to go ahead and take that number and turn it into a density, because later in the problem this becomes more useful. So I'll just label it as rho air. And in order to do that, you just take the reciprocal. Okay, so in order to go ahead and solve the rest of this problem, what I needed to do was find the rho of air, which I already said is 1.87 kilograms per meter cubed, and then the density of water, water vapor in particular, because it'll be in the air, and in order to be in the air, it has to be in a vaporous state. And so that is going to be 0.0831 kilograms per meter cubed just from the steam tables. And then I went ahead and added those, because if water vapor is in the air, then the total density of the gases in the system would be the density of the air plus the density of the water vapor. So when I added those numbers together, I got 1.947 kilograms per meter cubed. In order to find the ratio of mass that's then present of the water, you can simply take the rho of water vapor and divide it by the total rho, which reveals that mass, the ratio of mass, which I'm just going to label it M, it comes out to be, all right, So the answer to part B of the problem as a ratio is 1 kilogram of water to 23.95 kilograms of saturated air. So that means that for every kilogram of water, you need to have 23.95 kilograms of saturated air in order to hold it. So for C, it's literally the exact same process, except the value for, let's see, the values for V1 change because the temperature changes, and the value of the water density also will change, also because of temperature changes. Okay, so after going ahead and solving for the new specific volume, I find that it is equivalent to 0.8159 meters cubed per kilogram, and that's for air, which isn't a huge difference, but the bigger difference is in the water vapor. The water vapor's new specific density is 206.136 meters cubed per kilogram. So I'll do the same thing and turn those both into densities, add them up, and find the ratio. So at this second temperature of 0.01 degrees Celsius, you find that in order to hold the same amount of water, 1 kilogram, it requires about 10 times more air by mass, because it's 254 kilograms of saturated air. And this helps explain the last question, because assuming the composition of your breath does not change, what is the reason why your breath could immediately condense at 20 degrees Celsius but not at 0.01 degrees Celsius? This would be due to the fact that water cannot be held in as large of quantities in cold air as it is in warm air. This is just a property that accompanies condensation, and yeah, that's it.